previous session, we were looking at the various layers, and we considered the convolutional layer first of ACNN, which performs the convolution of the input image with a image filter, because it filters out some of the features, and the features that passes to the filter are catched on the other side. They will be caught on the other side, and you'll be representing them by the name called feature map, right? So we then saw an example like this. So there is a dog's input image, right, which will be passed through several uh, filters in the convolution layer by performing a convolution followed by an activation function. So the activation function's result will be again shown there, right? So you can find out many features that come up as a feature map. Right. Then we took an example and we tried to perform uh, the various type of operations, right? And we understood how to get the feature map and what are the specifications of this feature map. That also we have seen. And we observed that in the feature map, right, wherever whichever parts of our input image matches to the filter, you get a higher output value. Okay, and if it is not going to match, you get a lower value, right? So that example we had seen and we understood what exactly is happening, right? So to analyze that, we actually have performed the convolution of two different filters. Okay, then moving ahead, then we look at the second layer, that is called as a pooling layer. So pooling is basically combining of all the neighboring pixels into a specific representing value. How to find that? We understood we can do that by using varieties of operations, such as many. You can group the pixels and find the maximum, find the minimum, and many other things. Okay, so like that we can. This is what we observed, right? So also we saw one example, right, which explains how to do the pooling operation. Right. So after pooling, now we have to write a code to perform all these operations. As I told, our intention is to implement a deep neural network that takes an input image and recognizes the digit, whichever image that is contained in this. So we'll try to do that. So for example, I'll try to show you the data set which we are trying to use here, right? Okay, so I'll just paste a data set, a sample of our data set. I'll give you the details of the data set later, but as of now, let's just try to look at a sample data set. So it's not that the digit classification which we did earlier, right? So it's not that, it's actually a handwritten data set. It's actual images, right? Not a binary image, it is actual image. You can see that this is the data set which I'm talking about. So this is the data set which is taken from a very standard database, internationally available dataset from website. It is called as MNIST database, where you can find out many handwritten documents, right? So one of such document contains 70,000 images of handwritten letters, English numbers specifically. Okay, so 0 to 9, right? Total 70,000. Okay, right. So it's a huge data set. Now, if you consider each image, right? So again, here we are showing only a part of the image. 1 0 is one image. Okay, single 1, single 2, 3, 4, etc. So what is the size of each of this image? Each image, right? So each of the image here, right, is a 28 into 28. Okay, each image is 28 into 28 in size. So if you were to try to write a matrix for 0, it is 28 rows and 28 columns. Okay, such data. So you see that each data point itself is 28 into 28 pixels. Okay, it's black and white, so you are going to have only zeros or ones once again. So this is our fundamental problem, basic problem, something like application type. So what we solved earlier, right, so that was not of this level because that consisted only 5 into 5. Again, there were only 5 classes. How many images you had? You didn't consider many images, right? Very, very, some 5 or 6 images we considered. That was a very small data set. But now you see we are going to build something big now. So 70,000 images we are going to have. Okay, I'll show you how to collect them, how to get it into the computer, how to load it to the Matlab, etc. Everything will be showing. Okay, and then uh, we try to do the training as well as the testing now. So we know that training needs more data, testing needs lesser data. Right? So what we do, we split the 70,000 data that is present in this MNIST, right, universal data set. We split the 70,000 into 60,000 for training and 10,000 for testing. Okay, so this is the details of the data set which we are going to use. Right now, so let us say uh, we are trying to first initial phase. I would recommend this phase. So what we can do is instead of considering the whole 70,000, anyway, ultimately we are going to do that. But initially, let's take some 10,000 data. Let's say, okay, in the 10,000, 8,000 let us use for training, 2,000 for testing. If that gives you a good result, then our network architecture is good. We can do the training and testing of all, right, 70,000 data set at a data stage. Okay, this is what I prefer now, because I if you want to train with all 70,000 data, it's going to take a lot of time, right? So it may not be very efficient. Maybe that's also another reason. So what I suggest is let us just try with the 10,000 data initially, and once it is done, right, then we will try to implement using something using a bigger data set later. Okay. All right. So that's the first part. So we'll take 10,000. We'll download all the 70,000 data. That's for sure. But out of that, we'll take 10,000, split it into 8,000 and 2,000. So total 10,000, split it in the ratio 8 is to 2 or 80 is to 20. 80 to 20 ratio is a most recommended way for machine learning and deep learning algorithms, right? Then, right, perform training with 8,000 data, right? Then the testing should be performed with 2,000, right? So we will evaluate the performance of our deep neural network. Again, our intention is to implement the deep neural network with what? With a CNN. So as we know now, CNN should have internally two parts. One is the convolutional layer, and the second layer is the convolution followed by the pooling. Right? Then you will build another part of the circuit or the neural network, which is responsible for uh, the recognition part or the classification part. All right. So this is what is the details of the data set. Now let us go ahead, right? Let us see what type of convolutional neural network we are supposed to implement, right? Let's look at the data size. So each digit what you see here is a 28 into 28 black and white image. So which means there should be 28 into 28 input neurons, right? Just to collect the inputs, I need how many neurons? I need 28 into 28. So recall what we did in the right other code when we tried to classify 0 to 5 digits, right? 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. We tried to classify. So input was 5 into 5 image, which means we needed 25 input neurons. So likewise, we need now how much? 28 into 28, right? So 28 into 28 is 784. Fine. So, right? So how many input neurons? 28 into 28. Followed by, right? We need, so as soon as this comes in, we apply this to the convolutional neural network. So there is no feature extraction. Feature extraction should be performed by the uh, convolutional layer. Okay, so what we do, we try to use say 20 different convolutional we'll have a single convolutional layer that contains 20 different filters. Like yesterday's problem, if you recall, we used only one filter or two filters. One filter was 1001, second filter was 0110. Like, right? So those were the two filters we used to understand the concepts of how the features are getting extracted to get a feature map, right? That's what was the case yesterday. But now you see, we are going to use a convolution layer, single layer that has 20 different filters, right? Now, what will be the ideal size? Okay, what should be the ideal size of, right, the layers? So the idea is this, right? If you have something like uh, this scenario where I'm trying to classify, say, how many classes you have at the output, I have 0 to 9, so total 10 classes, correct? So we expect something like double of that. So 10 classes, double of that is 20. So I'm expecting 20 different filters. Okay, this is just a rough work, right? You can make a note. This is just a rough work, rough calculation. No, I have not made any markings so far. Okay, I'm still showing you the diagram, right? I will whatever I'm telling now, I'll write it later. Okay, I'll just show you one table. Okay, that table will contain this, but as of now, I have not made anything. I have not written anything except this diagram. I think you can see the data set itself, right? 0 to 9, several columns. Okay. Right. So I was trying to explain how to decide the number of filters. Right. Now, how many classes you have, irrespective of what is your the data set size. Now you can identify that I have 10 classes over here. So roughly, rough estimation is 20 filters. Right. What should be the size? Normally, size is you can take any odd number, right? Like you can start with the 5 cross 5, 7 cross 7, right? 9 cross 9, 11 into 11, and so on. Okay, so we'll decide that later, right? And obviously, the activation function need of this convolution layer has to be the ReLU layer. It's a ReLU activation function. Now, after the convolution layer, we have a pooling layer coming up. You have to decide what you do, right? Pooling is important, and normally pooling will not be of larger size. You can keep the standard one 2 cross 2. If at all it does not work, you can go for a 3 cross 3 and so on. Okay, always it is suggested to start with a smaller size of pooling. Then comes the classification. You can decide any number of layers, right? So if you have 10 classes, 10 times of that. Previously we did the same thing. So if you recall, so I had 5 classes, so I multiplied by 10, so 50 hidden layers were decided that case. Now I have 10 classes, so I'm going for 10 into 10, so 100. Right? So I'm going to have 100 layers of hidden, right, neurons. Followed by, again, you have to decide what is activation function. So by already we know that we have to use the ReLU activation function over there. Then you have the final output layer. Output layer, the size of the layer is equal to the number of classes you have. How many classes we have here? We have 10 classes. So because of that, now we are going to use 10 classes over here. So 10 output neurons. So whatever we discuss now, I'm trying to paste that over here. So you can consider this as our design of the deep neural network, which is implemented by as a convolutional neural network. Okay, so input size, you can clear it should be very clear now. Whatever I told, I have pasted down. So convolution, right, should be 20 filters, right? We'll take somewhere in the middle, so 9 into 9. Activation function, read, followed by pooling layer. Start with the smallest one, size 2 close. So there is no activation required. followed by the hidden, right? 100 nodes, it's obvious because 10 times the size. So that's why it is 10 into 10, 100. And output, number of output nodes is equal to 10. Okay, so I would like to paste another diagram over here. So which should give you a rough idea of what is the architecture that we are talking about right now. So this is the architecture. So the architecture actually shows multiple layers and it should look something like this. Okay, so we can see that there are many layers. The weights are actually required to be trained out of these many layers, only few layers. Okay, one is, you can see the weights W1, right? So that W1 is because of the convolution layer, because what are the values of uh, the filters that you should use for convolution needs to be identified. Okay, so that's the first objective. And the second one is, you can see that there is a the W5 written over there. You can see here, right? This is the W5 written over here, and the W0 at the output. So W5 and W0 contain the connection weights of the classification neural network, which is at the rightmost side of the uh, deep neural. And W1 is the weight that is required for, right, updating, or the during the training we update these weights and they form the weights of the convolutional neural. Okay, all right. So overall, that's the picture. That's the big picture. Right now, so let us move on and let us try to implement this on a MATLAB screen. Now, our first objective is to update all these weights, right? Initially, I'm starting with from there. So the input nodes between the pooling and the hidden layer, which are connected in the form of a square nodes, that's a W5 block, right? So let's try to write a function directly to implement this, right? So we'll go for the edit. I'll call the name of the function as MNIST convolution. So let's open up. All right. So let's start with the function. This is going to return those values, right? So what are the values we have written? We call it as one of them is W1, right? I'm trying to implement exact thing from the diagram. Okay, whatever was shown in the diagram, I'm trying to implement that same thing. So you can just refer this. So there is W1 over here, W5 and W1. Those are the values which I'm trying to update now. So I'm writing the code for the same purpose. All right, so what are the weights you are trying to update? First one is W1, followed by I write another weight that is W5 and the W0. So I'm expecting them to get updated after I run this code. So the name of the function is given as MNIST com, right? So you have to tell what are the parameters you're going to pass. I'm going to pass the same initialized parameters such as W1. Then I pass the W5 followed by W0. You have to pass it. In addition to this, pass the input vector X and the desired vector. That's a type. All right, so we passed. all of them will be passed. So they will go to the network. Okay, now, so let's write the initial value. Let's initialize some of the values like alpha. We require alpha, right? So alpha value, initialize that to be, maybe I start with a small possible value 0.01, and I'll also define, say, beta. Let's define beta is equal to 0. Maybe 95. Anyway, we'll verify whether this works. If it is not, anyway, I know that I have to tune the hyperparameter. Then we'll define some of the other terms which we already have defined in the previous classes. One is momentum. Define the momentums of various layers. Okay, so whatever is the size of the layer, so much momentum is required. So I'll call the first one is momentum 1 to be equal to, you initialize with the zeros. Okay, zeros, and how many zeros you should put, the whatever is the size of, right, uh, the first one. So I think we call first one as w1. Okay, that's momentum. So let me define the momentum. Second variable is 5, corresponding to 5, so I'll initialize in the same way. This is zeros, the size of, say, w. Okay, then let's go ahead. The momentum 0. Okay, that is equal to zeros of size of w0. Yeah, so we define this. Then let's define the n. So let's put n as the whatever is the number of elements in D, that is the desired vector. So whatever is the size, let me try to do. Then followed by, let me say, I'll define a B size. Okay, this is a batch size. I know that I have to give it in batch. So let me define it as 100 initially. Anyway, you can change it. So list. So I'll make a batch list. So we actually had studied many concepts here. We try to club everything here because this one particular mini project, I want you to include each and everything, right? We studied right from beginning of the deep learning concepts, right? MLDL, we started with the neural network. We saw the problems with neural network. We gradually increased the various terms and various issues, and we resolve the issues by bringing many terms, new terms such as momentum, batch size, etc. Right? So everything you can see here. All right. Okay. So I'm going to make a list. So this B list is equal to, starting from 1, right? I want to go till the B size. It's a size of, in the batch size. I want to go till the last number. So that should be n minus the B size plus 1. So because I'm eliminating the 0th index, so I have to add 1 to this. All right, so n minus B size plus 1. So if you prefer, you can definitely put a bracket to this last. Okay, so B list will start from the 1. It will go till n minus B size plus 1 and up to the B size. Okay, all right. So let's start with the epoch, right? So I'll just make a marker here. So this is my one epoch begins. I start my training process. Okay, only that this is just a marker for that. I'll just, when I look my code back, I just want to make sure that, okay, this is where it begins. Okay, only for that reason. Later on we'll remove this. So I'll start with the for, right? I have to do this many times. So for, let us start with the batch. Batch by batch, you need to perform this. That's why I give the name as batch. So for batch is equal to 1, starting from 1, and go till the length of this particular list which we have already prepared. So it is length of the B list. Until there, you have to do something. Okay. So, okay, for this, let me go with the DW1. Okay, updated one. Initialize. So many weights needs to be updated. So this should be zeros of the size of W1. Similarly, I have to do with the DW5 is equal to, this is zeros of size of W5. Okay, repeat this. I have to do for the W naught as well. So this is DW naught to be equal to zeros of size of W naught. Okay, that is done. Now I actually go for one batch. What happens in one particular batch? You see, you divided the whole bunch of your data set into so many batches. So once all the batches go, one epoch is completed, right? So that's the concept. Now, this for loop which we started over there is nothing but it is the starting point of my the every batch. So it's a epoch. Now inside epoch, I have many batches. So right now what I'm trying to write here is the code corresponding to that. So I'll make another mark here. This is just a marker, right? So this is my mini batch loop. That's what begins now. All right. So this is the mini batch. So I'll start with this. So begin equal to the list of your batch. So I think I gave a name as batch itself. So let me use that. Okay, so begin is from there you are trying to begin now. This batch begins from here and goes till where you use a for. For let's use, I think I use batch is equal to earlier, right? So for batch is equal. Okay, I can use any other number. Maybe for k is equal to, start from the begin, which you have just initialized, right? Increment, right? In the same size, right? Okay, I don't want increment. I want increment by one. And I want to go till the begin plus the total size, P size is one, right? Until the one before your next batch. So till there you have to go. Okay, now so you do now, you know, now you understand what we are trying to do. Small x is equal to the capital X of, I'm extracting one by one. Okay, so all the rows, all the columns, and kth particular page. This is what I'm trying to get. This is the X. Define y1 is equal to what I'm supposed to do. I will call my layer by a name called my convolution layer. All right. So to this, pass your input as well as the weight. We denoted the weight as W. Okay. Y1 is that. So whatever Y1 you get, this will be passed to the activation function. Let me call the output of my activation function is Y2. Y2 will be the ReLU. I think already we have written my ReLU. Okay, we already have a function called myRelu. Let me just verify whether the name is correct. Otherwise, it will throw up an error at a later stage. I don't know. I think we have a, so yeah, you see here, this is the myRelu is there, right? So I'll directly use it. So this is my ReLU of y. So I passed and I got this, right? So I get a y 2 at this. So after convolution, what do you expect? Convolution should be followed by a pooling layer, correct? So I have not written the pooling, but anyway, so let me call that function directly before I use it, before I define it. I'll define it later, okay? Right. Okay, so y3 is equal to, I'm going to pass it through a pooling layer, so I call it as my my pooling. This is the function which I'm going to write here. Okay, so this is the my pooling layer. Which one you pass? You pass y2 to through that. So y2 will pass through the pooling layer and you get a y3. So now you see, I actually have to make a change, right? That I'm going to have a, because pooling layers output will be multiple filters, right? I'm going to get multiple feature maps at the output. I want to club them into a single page. So you have multiple pages. All pages I want to put it into the same page, right? So that is what I'm going to do in this state. So y4 is equal to do a reshape. Okay, so this is reshape of which one, which variable? Y3, right? Y3 comma, make the second one null and the third one as 1. All right, so anyway, you understood that what are we are trying to do, right? Y3, right? Doesn't matter how many rows you have, you need to have one over this. That's the third variable. Okay, so you perform the this thing. So you see, okay, I'll try to trace out after I write this part of the code, what exactly is going to happen, right? I'll try to write as a comment on the right side so that we can verify whether the same thing is happening or not when we execute the code. Okay, right, okay. So let's say I got a y4 is the output of the pooling layer, which has been reshaped to a new value, right? And then I will simply multiply the w5 with the y4 to get v, maybe this is my v5. Okay, v5 is equal to, it's a weight into the input. So weight is nothing but, if you remember, this is w naught. W naught, you should multiply this W naught with the previous output. So that is a Y5. Is it Y5? My mistake. Sorry, this is Y4, right? Because I don't have a Y5 yet. Y5 yet to be calculated. Sorry, mistake. I'll update. This is Y4. Kindly note. Okay, so we got a V5, right? Uh, sorry, I think I need to verify the diagram once again. So I think I made a mistake. So see here, first is W5, then the W naught. Sorry, I think I wrote W naught now, which is my mistake. That's what I was thinking. So you see here, the W naught, which I have written here, right? This is not correct because first I get W5. So W5 into Y4 gives me a V5. Okay, I think this is correct. Right, I got this. Right, I got V5. How do you get the Y5? You have passed the V5 through a activation function, which is the ReLU function. So my perform this. So my ReLU, okay, ReLU LU is capital, so otherwise it will become error. So let me update even in the previous case if this is my ReLU. Okay, so this is my ReLU of the previous one, that is I think V5. Right, okay, this will pass through the ReLU to get a Y5. What should you do with the Y5? Pass it with the final, the output layer's weight. I'm going to call the output as V. Okay, V is equal to W naught into W naught multiplied by, I think Y5. Okay, right. So now you get a final output y is equal to, right? I think we already have a function written over there for softmax. Yes, we have. Let me use that. Okay. So this is my, so my softmax of the b. I hope this step is fine. Okay. Now let me try to trace out what exactly is going to happen here. Right. Let me write as a comment. Let me try to trace out, is it right or not? We'll see when we uh, execute the code. Right. What is the input size? So this actually is, uh, it should be comment. Yeah. So this is the comment. So this is inputs. What's the size? Is equal to, I think, 28 into 20. This is what is going to come. All right. So below that, right? What should you get at the output of convolution? I think I already mentioned a size. Okay. So I can write here, this is the convolution layer. I am expecting 20 filters and the output should pass through each of them. So I'm expecting 20 into 20 into 20. We'll verify this. So, so this is 20 into 20 into 20. Let's see. That's right. So then I have the ReLU layer. Anyway, ReLU will generate the same size, so it doesn't matter. I will come to the pooling. So what I'm expecting in the pooling is, so you see, this is actually a pooling layer, right? And I have 10 classes of 10 such size into maybe the 20 which will come over. So this I can write 10. It's a lesser in size. You can see that 10 into 10 into the 20 different ones. So reshaping will do this 20 into, see, reshaping is what you are trying to do here in the reshape. Everything you are going to put in the same this thing. You see, irrespective of the number of columns, only one number of rows, only one column. So 20 into 10, 200 into 10. So this is 2000. I'm going to get a 2000 data. This is what I'm expecting. Let's see. According to this. Then this is done. The ReLU softmax, yeah, here I can specifically say that I'm going to get exactly 10 classes over here. So I'm not very sure about this. I'll decide and I'll update what happens with this. V5 is equal to W5 into V4. Okay, because W5 is the size of 100 layers. So 100 layers means, okay, let me decide that later. Oh, this is what is the size I'm expecting now. Let's see what's going to happen, right? Okay, now, so I have to uh, perform every step that I decided earlier, right? Like I have to perform, right, the back propagation. I have to calculate the delta, right? Pass that delta to a hidden layer, pass that same thing to the layer before that, which is the previous layer, that is a pooling layer. Before that, you have a convolution layer. Pass your error through everything, right? So this is what is required. I hope you are fine with that, right? So the concept, it should be, you should remember the concept. Code can be written in any fashion. This is not the only way of doing the code of whatever is our problem. You can do it in any other way as well. Okay, but remember the concept, like, okay, I passed my input, I got an output. I have to use this output, right, to update my weights. That's my overall idea. Okay, right. So before that, I will define the required spaces now. So let me make sure that the d is equal to the zeros of, uh, I have to decide what is the size, right, of my output. So size of output is 10. There are 10 classes, one column. Okay, and I actually have to make the classes like this. So you do this job. So this is d of, I'll perform a modification that is sub to ind of the size of d, right? This is the size of d. So many values are there, right? Comma, I see what is there in my capital D. So that is D of K, because the index of the current loop is K, comma, 1. That's a third dimension, right? Make this, right, D as 1. Okay, so small d, wherever it is actually matching to the class defined by the capital D, you make it 1, others will remain 0. Okay, so that's the job of this particular. Okay, now let me just verify if it's showing a red color. I think I need to close another bracket here. So that's why it is showing an error. So I'll close it. Yeah, you see, now this is equal to 1. Let's move further. Now, actually, I'm starting with the back propagation, right? So error will be equal to the d minus y. Okay, calculate delta. How do you calculate delta? I know that, right? Because of the concept we already have studied, for the final layer, d has to be the error itself. You don't calculate a gradient, you directly assign. Then you go to the final layer's error, right? The error of the final layer, that is a hidden layer, or I think you can call it as a ReLU layer, that is E5. W5 was the weight, so E5 is the error. This is equal to the out, the weight after this layer is W0, right? Take that, and I think I need to transpose that because of the restrictions of matrix multiplication. Same thing we did earlier. Okay, this should be multiplied with the delta of the next layer, which is delta itself. Okay, once you do that, right, the delta 5 needs to be calculated. From the E5, you calculate delta. How do you do that? Do the same thing. All the values of Y5, this is the ReLU, right? Y5 greater than 0, you extract. Okay, all the Y5s greater than 0, you extract, and then you multiply. So there are many numbers, so it should be point by point, the dot product. That's why you have to write dot star the error, that is E5. That's E5. Then go for the layer previous to that. I'll directly write it as E4. E4 is equal to, look at the weight, that is W5, take a transpose, right, and multiply with the previous that delta, that is delta 5. So see, the same process is going to be performed again and again. So after E4, I'll go for, see, there is no delta because it is a pooling layer, right? It's just a pooling layer, so don't calculate. So go to the E3. All right, so E3 is equal to, perform the, because previously you have done a reshape, now you do the reshape back. All right, which one? The previous error, that is E4. Perform this into the size of, look at the previous one which you tried to reshape. I tried to reshape the Y3. Right, now I have something like this. I want it back into this size, that is Y3. So size of Y3 you can write. In the sense, convert E4 into the size of Y3. That's all. Okay, fine. So let's move ahead. Now after E3, my intention is to go to the E2. So you remember one thing here, wherever the weight is updated, then only you need delta 1. Otherwise, no delta. Okay, I'm simply calculating E3, E4. After E4, you see E4, E3, E2, no delta calculation. All right. Okay, so E2, let's calculate, right? Keep it as initialize with all rows. What is the size? It should be size of the Y2. So as many y2s you have, you should have same number of, okay, that is e2. Now let's go for the weight, that is w3 is equal to create the ones of certain size, right? What is that? That is the size of the y2, and I want to divide this by the size, which is 2 cross 2, right? So simply write 2 cross 2. Okay, this is done. Calculated w3. Now you update the w3. Okay, so let us try to do that. So w3 is defined. Okay, I think I should do it for, because there are 20 such values to be updated for error 2. So because e2 is a layer where you have 20 different values to be calculated. For c is equal to, starting from 1 till 20, perform this. So e2 is equal to, or okay, I'll give an index now so that it becomes easier for me to trace out. Okay, so all the rows, all the columns, and seed page of error should be equal to. So this is a function of e3 of all the rows, all the columns, seed, this thing, comma, once of, let's try to write the size 2 comma 2. So let me close this. I want to multiply this with, so dot star, the weight of the previous layer which is defined. So w3 of all the rows, all the columns, and C. Okay, so you are able to calculate uh, the E2 now, right? So this repeats 20 times, so that gets finished. Okay, now what you do? My previous layer has a convolution layer requires what you call as the weight updation. So I need to go for delta. This is delta 2 is equal to, do the same thing we did earlier. Take its output, that is y2, find out whether it is greater than 0. Only greater than the zeros will be considered in case of ReLU. Right? That's dot star e2. So that's the ReLU's layers data delta corresponding to my convolutional layer. I can have another delta. I call it as the delta. Let me write it as x, because another delta is going to come later. So I'll hold on to this. So delta x is equal to, put all the zeros of the particular size of, so look at the size, it should be the size of the w1 itself. Okay, so right, sorry, size I already have written, so size of w. Okay, so that's the size of w1 which we are talking about. So we will be able to calculate the delta x specifically. This is initializing. Now I calculate. So for c is equal to 1, how many such values to be calculated? 20 such values. Okay, so delta x should be equal to, again I think I need to give the index, define the indexes. So all the rows, all the columns, and the seed page, this should be equal to, right, I will see, now I'm bringing the convolution concept. You just see here, which is a function, inbuilt function, conv2. Okay, conv2 bracket, define the first variable, that is x of all the rows, all the columns. first variable. Come on, what is the second variable? Right, it should be the delta 2, right? Whatever delta 2 we have calculated, that should come now, but I have to rotate. So this is ROT 90. I have shown this. I showed you this uh, in the manual calculation. Right, there is a rotating 90 degrees option. Right, of sorry, the delta 2 of all the rows, all the columns, each particular page. Rotate this twice. That is a 180 degree rotation. Comma. Now you tell me which option I should use here. What type of convolution do you want? I'm actually reducing the size, right? So size gets reduced, so I should use valid. All right, so I use the valid option. So that's the calculation of the delta value. Right? So that finishes this calculation. Now you update your weights. So dw1 is equal to previous values of dw1. To this, I should add plus the delta value. Delta, I think I call it as delta x. All right, that will update this. Then dw5 will be updated later. So dw5 is equal to dw, that's a delta. Is it delta? Sorry, my mistake. I have to add, right? So this is dw5 plus the delta 5 uh, multiply this with the next layer. So it's y4. I need to take a conjugate. If you remember, this step is there. Okay, you have to take a conjugate followed by. So this is dw0 is equal to dw0 plus the first value of delta was simply delta, right? The final layer. So this is the delta. To this you multiply by 5, right? Take a take a transpose. Let me just verify delta 5 and delta I used for y4 and y5. Okay, this should actually finish my another one, the for loop which I started over there. Okay, so this has to be done. This loop I closed. Okay, one batch is over. This is repeating so many times, all the batches get over. Okay, now you see I have to perform what is called as batch normalization. We have studied that concept. So let's try to implement that. So, right, updating the weights will happen only after I use this. So perform the batch normalization. So dw1, whatever you got, should be equal to dw1, divide that with the b size, batch size. Okay, batch normalization. Do this same thing. So that is dw5 is equal to dw5 divided by b size. Okay, then dw0 also should be repeated with the same values. Okay, so that is dw0 to this divided by the b. Okay, that is done. Let's move on. One more last step is remaining. If you remember, I have to do the momentum. Why the momentum is required? It takes care of all the past learning updates. Okay, it gives a direction for your learning process. It will not randomly update your weight positive, negative, positive, negative. It will be updating in the same direction, and we understood that momentum is very stable. So we have to use that concept of momentum. Momentum 1 is equal to, if you recall, this is the equation, you use a alpha value. Okay, multiply the alpha with the change in the weights, that is dw1, right? Plus you already have defined a momentum, to that multiply by beta. So beta times the momentum 1. That's all. That's the momentum. Use the momentum to update your weight. So W1 is equal to W1 plus momentum 1. Repeat this. The momentum 5 is equal to alpha multiply alpha with the dw5, and to this you add beta times the momentum 5 and update w5 should be equal to w5 plus momentum, right? Momentum 0 should be equal to alpha into dw0 plus beta times the momentum 0, I think, yeah. So update, therefore final weight W naught is equal to the W naught plus momentum 0. Okay, so this actually finishes what? This finishes, I'll put an end at the end of a batch, right? You have to do this, right? At the end of all batches, you have to do this. So this for loop is over now. Okay, that's over here, right? So that is done, which means everything is over. The learning is over. I can end the function. I just have to write end at the end. That finishes your function. Okay, so whatever we had studied so far, we tried to implement everything over here. Okay, every concept came in here, and I think this code should work. All right, and we'll see that, right? How much, whether we need to make any modifications here, or is there any changes that should be incorporated in the next class.